Welcome to Chapter 5, where we dive into the fascinating world of heat transfer. In this first part, we will focus specifically on the mechanics of conduction. There are three primary ways that heat can transfer from one place to another. These are conduction, radiation, and convection. Today, our focus will be entirely on conduction. So, what exactly is conduction? It is the process of heat transfer through a substance from a region of high temperature to a region of low temperature. Crucially, this happens without any bulk movement of the molecules themselves. The material stays put, but the heat energy moves. Let's look at how this works in poor conductors, like nonmetallic solids and fluids. When one end is heated, the atoms there gain energy and vibrate with increased amplitude. They bump into their neighbors, passing that energy along. It is like a microscopic relay race of vibrations, transferring heat from one end to the other. In metals, which are good conductors, the story is a bit different. Metals contain free electrons. When heated, these light, mobile electrons gain energy and zip through the material at high velocities, colliding with the solid lattice to transfer heat. While atomic vibrations still happen here, the free electrons do the heavy lifting. This brings up a common question. Why are metals so much better at conducting heat than nonmetals? It comes down to those free electrons. While nonmetals rely solely on the relatively slow process of atomic vibrations, metals use both vibrations and highly mobile electrons. This dual mechanism allows metals to pass on heat energy at a much faster rate. To quantify how well a material conducts heat, we use a property called thermal conductivity, denoted by the letter K. It is defined as the rate of heat flow through 1 cubic meter of a material when there is a 1 Kelvin temperature difference across its opposite faces. The standard unit for thermal conductivity is watts per meter per Kelvin. Let's look at the mathematics of this. Imagine a conductor with a cross-sectional area A and a thickness or length L. If one end is at a higher temperature, theta 2, and the other is at a lower temperature, theta 1, heat flows. The rate of heat flow, Q over T, equals the thermal conductivity K times the area A times the temperature difference, all divided by the length L. Looking closely at that equation, we can identify the three main factors that dictate the rate of heat flow. First, the cross-sectional area. A wider path allows more heat to flow. Second, the temperature gradient, which is the temperature difference divided by the length. And third, the nature of the material itself, represented by its thermal conductivity, K. Let's define a couple of those terms more clearly. The temperature gradient is simply the change in temperature over a given distance. When a system reaches a steady state, it means the rate of heat transfer has stabilized. No heat is being lost to the surroundings, and the temperature gradient across the material remains perfectly constant. Let's apply this to an example. We have an aluminum plate with an area of 300 square centimeters and a thickness of 5 centimeters. One side is at 100 degrees Celsius, the other at 30 degrees, and heat passes through at 9 kilowatts. By rearranging our formula to solve for K and converting our units to meters and watts, we find the thermal conductivity of aluminum is 214.29 watts per meter per Kelvin. In our second example, we want to find the rate of heat loss through a glass window. The glass is 6 millimeters thick with an area of 2 square meters. The temperature difference is 20 degrees, and the thermal conductivity of glass is 0.8. Plugging these values into our rate equation, we calculate a heat loss rate of 5.3 times 10 to the power of 3 watts. For our third example, notice we are asked for the total quantity of heat, Q, not the rate. We have a brick wall 12 centimeters thick over 1 hour. We must convert that 1 hour into 3,600 seconds. We multiply the rate equation by time, plug in our area, temperature difference, and the K value for brick, yielding a total heat transfer of 1.56 times 10 to the power of 5 joules. So far, we have looked at heat flowing through a single uniform material, but what happens when heat flows through multiple different materials connected together? Consider 3 plates, P, Q, and R, arranged in a series. Each has its own thermal conductivity, and there are different temperatures at each junction. We will explore exactly how to calculate the heat flow across these composite surfaces next. Moving right along to our next major mechanism of heat transfer, let's examine thermal radiation. Unlike conduction and convection, thermal radiation is the flow of heat via electromagnetic waves, meaning it doesn't require a physical medium. A hot body emits a mixture of different wavelengths, and the exact makeup of this mixture depends entirely on the body's temperature. At lower temperatures, objects mostly emit infrared radiation, but as you heat them up to high temperatures, they begin to emit visible light and even ultraviolet radiation alongside the infrared. Let's focus specifically on infrared radiation for a moment. Infrared is the portion of the electromagnetic spectrum that sits just beyond the red end of visible light. It extends from a wavelength of about 0.7 micrometers up to about 1 millimeter. This is the primary band of radiation responsible for the heat we feel from everyday warm objects. Because infrared is an electromagnetic wave, it shares many properties with visible light. It travels at the speed of light, which is 3 × 10⁸ meters per second. It can be reflected by mirrors and refracted by lenses. Crucially for thermodynamics, it causes an increase in temperature when absorbed by matter. It can also trigger photoelectric emission, and it affects special photographic plates, which is how night vision infrared photography works. Interestingly, while visible light passes through glass, infrared is largely absorbed by it, but it easily transmits through materials like rock salt and quartz. So how do we detect infrared radiation? We can't see it. One instrument is the bolometer. A bolometer features a thin strip of material connected to a Wheatstone bridge circuit. First, we measure its baseline resistance. Then we expose the strip to radiation. As the strip absorbs the infrared energy, its temperature rises. Because electrical resistance changes with temperature, the Wheatstone bridge detects this new higher resistance, confirming the presence of infrared radiation. Another detection device is the ether thermoscope. This consists of a tube containing liquid ether and ether vapor connecting two bulbs, one clear glass and one blackened. When infrared radiation hits both bulbs, the blackened bulb absorbs much more heat than the clear one. This extra heat causes the ether vapor and the blackened bulb to expand, pushing the liquid ether down on that side and up into the clear bulb. This elegantly demonstrates that dull, black surfaces are far better absorbers of thermal radiation than clear or shiny ones. For a more direct electrical reading, we use a thermopile. A thermopile is simply many thermocouples connected in series to amplify the signal. It has a set of hot junctions, labeled A, exposed to the radiation, and cold junctions, labeled B, which are shielded. When radiation hits junction A, it heats up relative to junction B. This temperature difference generates an electromotive force, or voltage, which causes a deflection on a connected millivolt meter. This brings us to a foundational concept, Provost's theory of heat exchange. Provost stated that when a body is in thermodynamic equilibrium with its surroundings, meaning it is at a constant temperature, its rate of emitting radiation perfectly equals its rate of absorbing radiation. A profound conclusion from this theory is that a good absorber of radiation must inherently be a good emitter. If it weren't, it would absorb more heat than it gives off, and its temperature would continuously rise above its surroundings, breaking equilibrium. We can prove Prevost's theory experimentally using a Leslie's cube. This is a metal box filled with boiling water, ensuring all sides are at the exact same high temperature. However, the sides had different finishes: dull black, white, and highly polished metal. When we point a thermopile at each side from the same distance, the galvanometer shows the greatest deflection for the dull black surface and the least for the polished surface. This confirms that the dull black surface, which we know is a good absorber, is also the best emitter or radiator of heat. Now we introduce the concept of black body radiation. A black body emits radiation whose wavelength distribution depends entirely on its temperature, not on the material it's made of. If we plot the intensity of the emitted radiation against the wavelength for different temperatures, we get these distinct spectral curves. Notice the three curves for temperatures T1, T2, and T3, where T3 is the hottest. Let's analyze the special features of these spectral curves. First, as temperature increases, the overall intensity of radiation increases across all wavelengths. However, the intensity at shorter wavelengths shoots up much more rapidly. Second, for any given temperature, there is one specific wavelength that has the absolute maximum intensity. Third, and very importantly, as the temperature goes up, this peak wavelength shifts to the left, meaning it decreases. Finally, the total area under any of these curves represents the total power emitted per square meter. This shifting of the peak wavelength is mathematically described by Wien's displacement law. It states that the wavelength at which a black body emits maximum intensity is inversely proportional to its absolute temperature. We can write this as lambda max times T equals a constant. That constant, known as Wien's displacement constant, is experimentally found to be 2.9 times 10 to the negative third meter Kelvin. Let's apply Wien's law to two extreme examples. First, imagine a black body at a stellar temperature of 15 million Kelvin. By dividing Wien's constant by this temperature, we find a peak wavelength of 1.93 times 10 to the negative 10 meters, which is deep in the X-ray region. Conversely, the cosmic microwave background radiation of the universe is at about 2.7 Kelvin. Dividing the constant by 2.7 gives a peak wavelength of 1.07 millimeters, placing it firmly in the microwave region. Wien's law perfectly explains why a piece of metal changes color as you heat it in a forge. As it gets hotter, it emits more total energy, becoming brighter. Initially, the peak wavelength enters the visible spectrum at the red end, so it glows red-hot. As it gets even hotter, the peak shifts to shorter wavelengths. It glows yellow, then white-hot as the peak hits the middle of the visible spectrum, and eventually blue-hot. This is also why the center of a fire appears white. It's the hottest part, emitting intense radiation across all visible wavelengths simultaneously, which our eyes perceive as white light. To be precise with our terminology going forward, relative intensity refers to the energy radiated per square meter per second for a specific tiny slice of wavelength. Total intensity, on the other hand, is the total energy emitted per second per square meter across all wavelengths combined. And a true blackbody is defined as an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence. It reflects absolutely nothing and transmits nothing. While a perfect blackbody is a theoretical concept, we can create a very close approximation using a cavity radiator. Imagine a hollow tin, painted dull black on the inside, with a single tiny hole punched in it. Any radiation that enters this hole will strike the inside wall. Most is absorbed, and the tiny fraction reflected will hit another wall, being absorbed again. After multiple reflections, essentially 100% of the incident energy is trapped. When heated, the radiation escaping from this tiny hole acts as perfect blackbody radiation, depending only on the cavity's temperature. While Wien's law deals with the peak wavelength, Stefan Boltzmann's law deals with the total power emitted. It states that the total power radiated per unit surface area of a blackbody is directly proportional to the fourth power of its absolute temperature. Mathematically, power equals the surface area S times Stefan's constant sigma times temperature T to the fourth power. Because it scales with the fourth power, even a small increase in temperature results in a massive increase in radiated power. Let's look at an example. Suppose we have a cylindrical lamp with a radius of 10 to the negative 2 meters, a very short height of 0.75 millimeters, and a power output of 1 kilowatt. Assuming it acts as a blackbody, we want to find its temperature. We use Stefan's law, substituting the surface area of the curved part of the cylinder, 2 pi RH. Plugging in 1,000 watts for power and Stefan's constant, we solve for T to the fourth, and taking the fourth root gives us a remarkably high temperature of about 4,398 Kelvin. In this second example, we link electrical power to radiated power. A filament melts at 0.4 amps and 240 volts. The electrical power is current times voltage, which equals 96 watts. We set this equal to the radiated power from Stefan's law. Using the filament's dimensions for surface area, we calculate the melting temperature to be 1,523.6 Kelvin. For part 2, we bring back Wien's law. Dividing Wien's constant by this melting temperature gives a peak wavelength of 1.90 micrometers, which is in the infrared range. We can also use these principles to find Stefan's constant experimentally, or to probe the stars. In example 3, a 10-watt lamp operates at 49% the efficiency of a perfect blackbody. By converting 217 degrees Celsius to Kelvin and plugging in the values, we can solve backward to verify Stefan's constant is 5.67 times 10 to the negative 8. In example 4, we estimate the surface temperature of the Sun. By using its mass and density to find its volume, then its radius, we calculate its surface area. Plugging the Sun's massive power output into Stefan's law yields a surface temperature of 5,840 Kelvin. Up until now, we've only calculated the power an object emits, but remember Prevost's theory. Objects also absorb radiation from their surroundings. If a black body at temperature T0 is in an environment at a lower temperature T, it emits power based on T0, but absorbs power based on T. The net power lost by the body is the difference between the two. We factor out the surface area and Stefan's constant to get the net power equation. P net equals S sigma times the quantity T0 to the fourth minus T to the fourth. Let's apply this net power formula. Imagine a spacecraft with a 25 square meter surface area kept at 300 Kelvin, flying through deep space, which acts as a 50 Kelvin environment. Using our net power equation, we find the spacecraft loses heat at a rate of 1.15 times 10 to the fourth watts. In a second example, an electric fire lamp consumes 1 kilowatt of power to maintain its temperature in a 20 degrees Celsius room. By setting the 1000 watts equal to the net power radiated away, we can solve for the element's working temperature, which comes out to 1170.8 Kelvin.
We can also determine how much energy is needed to maintain a temperature difference. If a copper sphere is kept at 127 degrees Celsius inside a 100-degree oven, it is constantly losing heat. Calculating the net power shows we must supply 1.779 watts continuously to maintain that 127 degrees. Furthermore, if we place a cold 150 Kelvin sphere into a warm 290 Kelvin room, it absorbs net power. By equating this net absorbed power to the thermal formula, mass times specific heat times the rate of temperature change, we find the sphere's temperature initially rises at 0.067 Kelvin per second.
Sometimes we need to compare two different scenarios using ratios. Here, a metal sphere cools at 3 degrees per minute. We want to find the cooling rate of a second sphere with twice the radius at a different starting temperature. Because mass scales with volume, doubling the radius increases the mass by a factor of 8, while the surface area only increases by a factor of 4. By setting up the net power cooling equation for both spheres and dividing one by the other, the constants cancel out, allowing us to solve for the new cooling rate, which is 0.48 degrees Celsius per minute. Up to this point, we have assumed our objects are perfect black bodies. In reality, most objects emit less energy than a perfect black body would at the exact same temperature. We account for this using a dimensionless factor called emissivity, represented by the letter E. Emissivity is the ratio of the power actually emitted by the body to the power that would be emitted by a perfect black body. We simply multiply our previous Stefan's law and net power equations by this factor E.
Applying emissivity gives us much more accurate real-world calculations. For instance, a 100-watt bulb filament with an emissivity of 0.70 means it only radiates 70% as efficiently as a blackbody. Factoring this 0.70 into our equation, we find the working temperature is 2020 Kelvin. This understanding of real-world radiation and power output leads us directly to the concept of solar power and the solar constant, which measures the exact amount of solar energy hitting a square meter of Earth every second. We will derive the expression for the solar constant in the next segment.
Let's examine the radiative equilibrium between the Sun and the Earth. The power radiated by the Sun is given by Stefan's law as 4 pi r squared sigma T to the fourth, where r is the Sun's radius and T is its surface temperature. As this energy spreads out spherically, the solar power or intensity at a distance r is this total power divided by the surface area of a sphere of radius r. The Earth intercepts a fraction of this power, equal to the solar intensity multiplied by the Earth's cross-sectional area, pi r squared. Assuming the Earth behaves as a black body, it also radiates power. At thermal equilibrium, the power the Earth receives exactly equals the power it radiates. By equating these two expressions and canceling out common terms, we can derive a simplified formula for the Earth's temperature. T to the fourth equals the square of the Sun's radius divided by twice the distance to the Sun, all multiplied by the Sun's temperature to the fourth. Using the equilibrium formula we just derived, let's estimate the Earth's surface temperature. We are given the Earth's distance from the Sun as 1.5 times 10 to the 11th meters, the Sun's radius as 7.0 times 10 to the 8th meters, and the Sun's surface temperature as 6,000 Kelvin. We plug these values into our derived equation. By squaring the Sun's radius, multiplying by the Sun's temperature to the fourth power, and dividing by 4 times the square of the distance, we get the Earth's temperature to the fourth power. Taking the fourth root of this result gives us an estimated Earth temperature of 290 Kelvin. We can apply the exact same principle to other planets. For example, let's estimate the surface temperature of Mars. The only variable that changes here is the distance from the Sun, which for Mars is 2.28 times 10 to the 11th meters. The Sun's radius and temperature remain the same. We substitute the new distance into our equilibrium equation. Because Mars is further away, the denominator in our fraction is larger, meaning the overall power received is lower. Taking the fourth root of the calculated value gives us an estimated surface temperature for Mars of 235.08 Kelvin. As expected, it is colder than Earth. Now let's look at a much more distant object, Pluto. The average distance of Pluto from the Sun is about 40 times that of the Earth, so our distance r is 40 times 1.5 times 10 to the 11th meters. We use the same equilibrium equation, substituting this much larger distance into the denominator. Because the distance is squared, the solar intensity drops off significantly. When we calculate the final value and take the fourth root, we find that Pluto's estimated surface temperature is a freezing 45.8 Kelvin. This clearly illustrates the inverse square law of radiation in our solar system.
Let's look at a generalized proof for mean equilibrium temperature. If the total rate of energy emission by the sun is E, the solar power per unit area at the Earth's orbit is E divided by 4 pi r squared. The Earth intercepts this energy over its cross-sectional area, pi r squared. At equilibrium, this received power must equal the power radiated by the Earth, which is 4 pi r squared sigma t to the fourth. By setting these two equal, we can cancel the Earth's radius squared from both sides. Rearranging the formula to solve for t to the fourth, we get E divided by 16 sigma pi r squared. This elegant equation shows how a planet's temperature depends directly on the star's energy output and inversely on the square of its orbital radius.
The source material provides a comprehensive set of practice problems in exercise 45. Let's review the first four. Question 1 asks for the temperature of a cylindrical electric fire element acting as a blackbody, which yields 1105 Kelvin. Question 2 involves a copper sphere, cooling in a specific enclosure, requiring us to calculate the initial rate of temperature rise using Stefan's law and the specific heat capacity of copper, resulting in 6.78 times 10 to the negative 2 Kelvin per second. Question 3 is similar to the first, estimating the temperature of a radiant wall heater's silica cylinder at 1073 Kelvin. Question 4 places a blackened sphere at the focus of a concave mirror directed at the sun, concentrating the solar power to achieve a massive maximum temperature of 2021 Kelvin. Continuing with exercise 45, question 5 asks for the power loss per unit length of an unlagged copper pipe carrying warm water, which comes out to 19 watts per meter. Question 6 involves finding the equilibrium temperature of a blackened metal plate receiving solar radiation on one side, resulting in 378 Kelvin. Question 7 is a classic radioactive equilibrium problem, asking for the Earth's surface temperature, which we previously calculated to be around 289 Kelvin. Question 8 requires calculating the new operating temperature of a car headlamp filament when its current and voltage are altered, relying on the relationship between electrical power and radiated power. Moving on to questions 9 through 11. Question 9 asks for the rate of temperature fall of a copper sphere. We are given the radiation rate at 0 degrees Celsius, which allows us to find the sphere's surface area or related constant, and then we apply the cooling formula for a sphere at 1000 degrees Celsius. Question 10 provides the solar energy received at the Earth's surface and asks for the effective solar temperature. This requires working backward from the solar constant to the sun's surface using the inverse square law. Question 11 asks us to estimate the surface area of a 100-watt tungsten filament operating at 1500 degrees Celsius, which is a direct application of Stefan's law, solving for area A. The final questions in exercise 45 cover a range of scenarios. Question 12 asks for the net rate of energy lost by radiation for two different bodies, a hot sphere in a cool room and a person in a freezing room. This highlights the net radiation formula, which takes the difference between the fourth powers of the body's temperature and the surroundings. Question 13 is another solar concentrator problem, using a concave mirror to heat a small metal sphere. Finally, question 14 applies Wien's displacement law. Given the peak wavelength for a black body at 1110 Kelvin, you must calculate the peak wavelengths for iron in a flame, a star, and fusion plasma, demonstrating how peak emission shifts to shorter wavelengths at higher temperatures. Now, let's shift our focus to the greenhouse effect. The sun emits short wavelength radiation, which easily passes through the Earth's atmosphere. This energy is absorbed by plants, land, and water, heating the Earth's surface. Because the Earth is much cooler than the sun, it re-radiates this energy as long-wavelength infrared radiation. However, greenhouse gases in the atmosphere, like carbon dioxide and water vapor, are opaque to these long wavelengths. They trap the outgoing radiation, preventing it from escaping into space. The continued accumulation of this trapped thermal energy raises the overall temperature of the Earth, a phenomenon that leads to global warming. Next, we explore thermal convection. Convection is a process of heat transfer through a fluid, which can be a liquid or a gas, from a region of high temperature to low temperature, driven by the actual physical movement of the medium. The mechanism is quite simple. When a fluid is heated from below, its molecules gain kinetic energy and spread apart, causing the fluid to expand. This expansion makes the heated fluid less dense than the cooler fluid above it. Because of buoyancy, the warm, less dense fluid rises to the top, while the cooler, denser fluid sinks to take its place. This continuous circulating current effectively heats up the entire volume of the fluid. A perfect natural example of convection is a sea breeze, which occurs during the day. Land has a lower specific heat capacity than water, meaning it heats up much faster under the sun. As the land gets hot, it warms the air immediately above it. This warm air expands, becomes less dense, and rises into the atmosphere. To fill the low-pressure void left by the rising air, cooler, denser air from over the sea flows inland. This horizontal movement of air is what we feel as a refreshing sea breeze blowing from the water towards the shore. At night, the process reverses, creating a land breeze. Because the land has a smaller heat capacity, it not only heats up faster during the day, but also cools down much faster at night. The sea, holding onto its heat, remains relatively warm. Therefore, the air above the sea is warmer and less dense than the air over the land. This warm air over the water rises, and the cooler, denser air from the land flows out towards the sea to replace it. This creates a gentle breeze blowing from the land out over the water. Have you ever noticed that cloudy nights feel warmer than clear nights? Here is the physics behind it. During the day, the Earth absorbs heat from the sun. At night, the Earth acts as a black body and radiates this heat back out into the atmosphere as infrared radiation. On a cloudy night, the thick layer of clouds acts like a thermal blanket. It reflects and absorbs the radiated heat, sending much of it back to the Earth's surface, keeping the environment warm. On a cloudless night, there is no barrier. The radiated heat. The source material concludes with a massive collection of past exam questions from the Uganda National Examinations Board, or UNEP. Let's look at the highlights from 2017 and 2016. In 2017, students were tested on defining thermal conductivity, explaining convection, and verifying Newton's law of cooling. They also had to calculate interface temperatures in a composite brick wall. The 2016 paper focused heavily on black body radiation, asking students to sketch intensity versus wavelength graphs, describe an optical radiation pyrometer, and apply Provost's theory of heat exchanges to a metal sphere in an evacuated enclosure. Moving back to 2015 and 2014, we see a strong emphasis on experimental setups and practical applications. The 2015 exam required describing an experiment to determine the thermal conductivity of copper and calculating heat flow through a double-glazed window. It also asked how a welder protects their eyes from intense black body radiation. The 2014 paper asked students to explain how a black body can be approximated in reality, to list the properties of ultraviolet radiation, and to calculate the sun's surface temperature using Stefan's log and the solar constant. The 2013 and 12 exams featured some challenging calculations. In 2013, students had to describe how a bolometer detects infrared radiation and calculate Stefan's constant from the cooling rate of a suspended blackbody sphere. The 2012 paper included a complex problem about an iron vessel coated with soot, filled with boiling water, and placed on ice. Students had to set up a steady-state heat flow equation, equating the heat transfer through the iron and the soot to find the interface temperature of 99.52 degrees Celsius, and then use that to calculate the rate at which the ice melts. In 2011 and 2010, the focus shifted slightly towards temperature distribution and radiation detection. The 2011 exam asked for a description of a thermopile and required students to explain the temperature distribution along perfectly lagged versus unlagged metal bars. It also featured a calculation for heat flow through a 2-layer furnace wall. The 2010 paper tested basic definitions of conduction, convection, and the greenhouse effect, and included a calculation for the power radiated by a gray surface that emits only 50% of the radiation of a perfect black body. Looking at 2009 and 2008, we see questions probing the microscopic mechanisms of heat transfer. 2009 asks students to explain thermal conduction in nonmetallic solids and why metals are superior conductors. It also required calculating the energy needed to maintain a copper sphere at a constant temperature in a cooler enclosure. The 2008 exam focused on the laws of blackbody radiation, asking for sketches of spectral distribution, and featured a problem calculating the surface temperature of a distant star based on the energy intensity received by an orbiting planet. Finally, let's review the highlights from 2006, 2005, and 2004. 2006 featured a composite wall problem with an air gap, asking students to compare heat loss through the air gap versus a solid brick wall. 2005 asked for an experiment to measure the thermal conductivity of glass and included a complex problem involving Y-shaped welded rods of copper, brass, and steel, requiring students to find the junction temperature. 2004 brought back the soot-coated saucepan problem, asking students to calculate the thermal conductivity of the soot based on the rate at which water boiled away.
To wrap up this final session, let's review our key takeaways. We've seen that radiative equilibrium dictates planetary temperatures. A body's temperature stabilizes when the power it absorbs equals the power it radiates. We explored how the greenhouse effect traps long-wavelength radiation, warming our planet. We also broke down thermal convection, seeing how density changes drive natural phenomena like sea and land breezes. Finally, our extensive review of past exam questions highlights the importance of mastering Stefan's law, thermal conductivity, and heat transfer mechanisms to solve complex multi-step physics problems.